recording. So Monday is a break, but then Wednesday is the exam. So I wanted to talk just a little bit about the exam. And if you have other questions, you could email me over the longer weekend. It's going to cover mainly Chapter 2, which is the R programming language structures and data structures and functions and so forth. And then it's going to cover up through not today, that is up to today. That in particular it's going to cover up through S3 classes, which is section 3 of chapter 3. But not what we'll be doing today, which is S4 classes, which starts in S4. So if you wonder what the types of questions will be, if you look at chapter 2, chapter 2 deals with the R language fundamentals, and it goes from fairly simple assignments and things to sequences, and data structures, of course, are quite important. Vectors being sort of basic, but then you have matrices, you have list, you have data frames, you have factors, and so forth. So you have different data structures, some of which are statistically oriented, like a data frame. A data frame is a construct that you could have in another language, but it's essential for statistics. You should know the distinctions between. In other words, some of the questions may be sort of conceptual, like how does a data frame differ from a matrix? Those types of questions. So those would be a descriptive answer that you need to give. On the other hand, I may give you some R code, and I may say, what does this R code, what's the output, or explain the steps. What is it doing? I could also give you some incorrect R code and say, why is it incorrect? And ask you to give the correct code. Any code I give will be pretty short. If I ask you to give code, it will be pretty short. It won't be a long function you have to write. There's not enough time for that. But I could ask you for the code in some simple cases. But in most cases, I'll give you the code and ask you what it does, or what's wrong with it, or what's the output, explain the steps. Most of it will be that way. But as I said, there could be some instances in which, I actually would ask you what the code is. So if you look through, all of chapter 2 is important. As you look through it, I think the only section that we had vectorized computation, replacement functions, subsetting, looping, functional programming, writing functions, flow control. The section that I did not spend much time on is section 211 on exception handling. We've had a few examples of that, but I'm going to talk a little bit more, and I've actually, as I said, we've had a couple examples about using try. It's called try catch, but I haven't formally talked about this particular section, so I don't anticipate that I'll be asking a question from section 211. 212, yes, that deals with evaluation, and there you're talking about statement evaluation as well as function evaluation. So you should understand those, and you should also understand the idea of namespaces and the scoping, the lexical scoping. We had an example of likelihood estimation. How do you write a function to get the maximum likelihood estimates? I didn't do much on graphics in 214. So again, you can kind of go light on the 211, I believe it was. On the exception handling. Is that it? Yeah, 211 and 214. But the other sections you should study. Now you're allowed to have, what did I say, a sheet of paper front and back? And that I mean a normal size 8.5 by 11. Okay. So a normal size paper front and back. How you do it is up to you. It's a good way to study, actually. You know, if you construct a really good sheet of notes, you probably can't do it unless you've sort of learned the material. So that's actually constructing a good sheet of front and backs is a pretty effective way of studying. Because A, you want to make sure that you have all the important ideas down. Magnifying glasses are not allowed. So in other words, sometimes if you try to jam too much onto those front and back, you spend all your time trying to find stuff. That's actually why I limit to 1 page. You know, because you start spending all your time looking through stuff. And then you don't finish the exam. So I want you to know the material. The idea of the notes is to jog your memory if you've forgotten something. There's a lot of little details. Are there questions on Chapter 2? In Chapter 3, well, Section 1 wasn't too much, just sort of some general ideas about object-oriented programming, and actually Section 2 is sort of the same idea. It gets into basic principles of object-oriented programming, no matter sort of what the method you use. They have similar ideas of inheritance, dispatching, you know, abstract data types, and so forth. Section 3 is the main topic, and that's for S3 classes. And so there's really 2 things that you have. One is that you had all the little aspects of, you know, classes, implicit classes, generic functions and methods, dispatching and finding methods, and so forth. So you had all of these. That section isn't all that long, but in addition to this section, you have your homework. By the way, I will send back your graded homework to you sometime over the next few days, so you'll have that to study with. But again, assignment 2, hopefully if you do that assignment, it's going to greatly help you in terms of this 3rd chapter, particularly, I mean, the S3 methods. If you try to work the assignment, it will challenge you to learn the ideas of S3 object-oriented programming. So even if you don't get everything right, you know, you're going to probably struggle with it a bit, and it's going to help. It's going to help you learn it. Again, also go back and look at. We did two examples. We did the t-test example, and then we also did Lin-Mon. So again, the exam's going to cover up through up to page 84. Now I want to give you a little bit of idea of where we're going to be heading. Right now I'm having an internal debate with myself as to how far I want to go with S4 classes. I'm going to cover them to some degree, and I'm going to do that today. The debate I'm having is, am I going to have you do the same assignment that you have for S3 classes, but do it with S4 classes? In other words, the one way that I'm having you do for using S3 classes, I could say, okay, redo this with S4 classes. That's a little more challenging, and that's my debate, you know, as to whether or not you know, that's something I want to have as a third assignment. And I haven't decided yet. If I do that, I'm going to have to give you an example, like the t-test example or something that sort of gives you the idea of the types of constructors that you need to do S4 programming. But again, S4 is not on this exam. Only to the extent that only to the extent of some general ideas of S4, which I've talked about in section 3.2. That talks about some general ideas of S4, but not the details. So I'm not saying I'm not going to have anything on S4, but it's only to the extent that the S4s are discussed in section 3.2. Getting into the details of S4, which starts in section 3.4, is not covered. So I may have some general questions about that are covered in 3.2 that sort of contrast what happens in S3 versus S4, but not the details. Okay? Now I usually also say work 12 out of 13, or something like that, which means that if I get 13, you can work all 13 and I'll drop your lowest question. So if you skip one, that's obviously your lowest. So, so I usually do something like that. Now how many questions I give, they're going to be short answers, a little bit of codes. Some cases you may have, a few of them you may have to write code, some of them you have to simply have the code and talk about it, what it does, and so forth. Again, what I call short answers. They're not true and false. They're not long coding examples. And so in that sense, it's a little bit like the first assignment, although some of those were probably more challenging than what I'm going to give because those were homeworks, not exam questions. So some of those ones that you found more difficult in your first assignment, you know, I'm probably not going to get ones that difficult. I just wanted to talk, are there any questions on the exam? And then I just want to say a few more words about where we're heading for the rest of the course. Are there any questions about the exam? Okay, I get partial credit. So you have partial credits, you're going to have like 12 out of 13 or something like that. And you got notes. So you're getting some help along the way. But having said that, R, I recognize, it's not a trivial language to learn. And getting into some concepts like lexical scoping takes some thought, or evaluation environments. Those are perhaps the most difficult areas that we've learned, the concept of environments and evaluation environments and scoping. Those are probably the most difficult topics. Looping can be tricky to make sure if you have a while statement, to make sure you stop correctly at the correct time. So, you know, the other thing's going to be a little tricky, but conceptually they're not as hard as things like scoping. Well, as I said, we're going on. We're going to be talking today about S4 classes, and some of the topics get a little bit more esoteric, and I may not spend too much time on it. And as I said, I'm trying to decide if I, want you to actually do an assignment on S4 classes, other than the fact that I may give assignments out of the book, or at least if I give an assignment, is it an out-of-the-book type assignment, or is it like the S3 assignment? Now, Chapter 4 is input and output. It's a shorter chapter, and it's fairly important in terms of reading stuff in and reading stuff out, getting stuff into R, and how do you export it, or how do you print things and save things and so forth. So it's fairly important, but it's not as long or difficult a chapter as Chapter 3 is kind of the core chapter. Chapter 5 is working with character data. Obviously in bioinformatics that's very important because you have you have sequence data, for example, that are letter. You can think of those as letters, and you have to manipulate that in search of things. So manipulating character data in 5 is important. Now, on the other hand, 6 is important, but it goes a little bit beyond what I want to do in this course. That's foreign function interfaces, and that would be that if you write C code or C++ code or Java code, how do you integrate it? I would probably give an example of that, but it's not going to be an extensive part of this course. You could actually pretty much do a whole new course. If you had a course on this, you'd pretty much have to teach people how to program in C and C++. And for those of you that are interested in that, there's a package that's pretty good that allows you to integrate C++. And so there's a book on this. And so for those of you that want more high performance, then I'm going to point you towards that book. So I may give an example, but I'm not going to spend a lot of time on Chapter 6. But for those of you that are interested, there's a pretty good book on it now, at least for C++. Chapter 7 on packages, you'll have an assignment on that because this one way that you've written the S3 classes, I'm now going to make you take that same structure that you've built and make a package out of it. So Chapter 7 is on packages. Now, Chapter 8 we're going to do as we have time. And the reason I say that, it's on data technologies. And we have a whole new course called Stat 623 called Data Technologies. Now, that particular course covers a lot of what's in this chapter and expands on it a great deal. That course is going to be refocused a little bit because there's now another book coming out dealing with web technologies using R. And that book is actually going to come out in early 2014. And so probably the next time we teach Stat 623, it's probably going to, there's a book called Data Technologies, but there's this new book coming out by Duncan Temple-Lang and Deb Nolan that I think is going to be quite good. Because R, if you're looking at, in general, there's huge resources out on the web, and so how do you get those resources? How do you manipulate them? How do you get them into R and so forth? And that's particularly true in the area of bioinformatics, where you have all these databases out there, and how do you get the data in? We're going to do some of that before the end of the semester. But again, we have a more advanced course that we also will be teaching that gets into these topics. That'll be next year, that course will be taught. The 623 and 624, and 624 is high performance computing with R, taught every other year. So, as we have time, we'll try to cover some of the material in Chapter 8. So let's, any questions on the exam, where we're going? This is actually taking us slightly longer to get through the programming. If I would be critiquing this book, so for example, in Chapter 2, we did the likelihood functions and so forth, which I think is good. But in this chapter, if you're really going to have a book where you want people to learn S3 or S4 classes, you've got to provide examples of the whole thing, not just little pieces of code. And this book doesn't do it. And that's why with S3, I gave you 2 examples where it does it, because otherwise you really can't program R unless you actually do a project. So that was the purpose of this S3 project. So let's go to S3 classes, and I'm going to go ahead and knit it. I was just showing that I actually can blow this up a little bit. You can hit the Command plus key if you have it on your screen. Yeah.
Are we going to use the computer in the exam?
No, you are not. No, it's on paper. No, you're not using a computer.
I mean, are we going to use our program?
You will have. I'll have paper with R code on it, or you may have to write a little piece of R code. Or I may give you code and I may ask you what it does, but you won't run it on the computer. You'll have to know what it does just conceptually. What's the output, or what does this statement do? Okay? So no, you will not use the computer. I'm glad you asked that question. It's an important question, actually. So we have these concepts with object-oriented programming. We have a class. For S4, you have representation, contains, prototypes, and validity. Those are the different components you need. And so when you are specifying a class, or when you're defining a class, there's a function called setClass. And setClass defines a class. In this case, for example, here, we have defined a class called A. And the representation are the slots. Those are really the data structures of that class. Now, a class is also going to have methods, but those are methods that act upon instances of the class. So we have a representation. In this case, we say we have a slot called S1, and the type of it is numeric. And then the prototype actually, is actually, when you create an instance of a class, it gives the default values. In this case, you would say that, okay, if I create an instance of a class with the function new, for example, then I will create an instance, and by default, the slot S1 will have value 0 because the prototype specifies those values for those slots. Now, you can override those in the new state. There are various ways you can override those default values in the prototype. Now, when you say prototype equals prototype, the second prototype is actually a function right here. It actually doesn't, that's not the only way you can define a prototype. You can define it as a list, for example. I could have a list, and the components of the list would be the slots. And there are certain advantages to doing this, as we may see later today if we get to it. So when I say prototype equals, okay, I have to define these default values somehow. And the prototype function is one way of doing it, but there's another way of doing it is to actually use list, L-I-S-T. And the list would have components where you define S1 as equals 0 as a component. And so I could do it that way also. So to create a class, I say I want a new A, and it's going to create an object. It's going to create an instance of that class, which is an R object, and the class of that object will be A. And we need to name, typically we're going to create this object and we need to actually have it, so I'm going to capture that object in an R object called myA in this case. And then myA says it's an object of class A, and it has one slot, S1, which has a value of 0. So I have an instance of the class A called myA. I could create other instances, but they would be separate instances, but they would all, by default, they would all have the value of 0 for the slot S1. But if I say new A S1 equals 10, and if I look at M2, notice that now I have overridden that default value of 0 by S1 equals 10, which is specified in the new statement. Okay. So if I go back and look at this, by the way, if I put my cursor in a chunk, you can simply go in and say run current chunk, and if I do that, it actually runs the whole chunk, which is convenient. If you simply want to run a chunk. You actually have other options. If you look at the RStudio, you can run the next chunk, you can jump to chunk, and so forth. You can also run the previous code region. So once I've run it, I can go back and rerun it. I can make a change and go back and rerun it. This run runs a line at a time. And of course, this does the whole file. So you have these options here. So, so if we go down and whoops, I forget it's in a tab. I keep thinking it's. Okay, so suppose we create a class B that contains A. Now, what we mean by that is that B actually inherits from A. So if A has slots, B can give additional slots, but it also has all the slots of A. So B may have additional slots, but all the slots that are in A are also in B, if B inherits from A. So sometimes it's counterintuitive. So it turns out that, for example, if I have an LM function, which means linear model in R, and then I have GLM, which is generalized linear model, you might think that linear model inherits from general linear models, but in fact, we usually do it the opposite. Because a linear model is sort of a special case, in a sense, of a generalized linear model. And so the inherent, if we have a linear model, a generalized linear model object, it actually not only has the slots that are specific to generalized linear models, but it also has the slots that are specific to linear models. And the reason for that is, there are a lot of reasons. One is that one of the generalized linear models, there are various ones like Poisson regression, binomial regression, but also normal regression. Well, normal regression is a linear model. And furthermore, even if you do something like a Poisson regression, I don't know if any of you have taken step 555, categorical data analysis. If you're doing a Poisson regression while you're trying to predict, let's say, a binary or categorical outcome, if you have these types of models, we actually approximate it by a linear model, and then we iterate over that to keep improving the approximation. Because generalized linear models have a linear component and a nonlinear component called the link function. So that they're sort of like, in some ways, a linear model. So we can actually leverage off what we've already done with linear models to actually do the computations for generalized linear models. And so when you're constructing this hierarchy of classes, it can save a huge amount of programming because you can use what you've done before. For example, if you had a structure built up for class A here, and then you do B, and B has some additional slots, everything that's in A is available to B. That's the reason they use contains, even though that may seem counterintuitive to you. So, so if I say set B and it contains A, that means that B inherits from A. And so in this case, we have another slot S2, which is character. And we specified a prototype of S2 equals high. So the question might be is, okay, if we create an instance set of new B, if you see, it actually, going back to, if I can find it here, I'll go ahead and run this whole setup, this whole chunk. If I create B, not only does it have the slot S2, which has a value of high, but it also has S1 from A, which has a value of default 0. So in other words, I inherited, or I automatically have those slots to define for A also. Is that clear? Okay. So that's something, we can actually build a whole tree structure where you have inheritance. And S4 also supports multiple inheritance. That is, a class can inherit from multiple places. Removing class, again, he recommends you don't really do that. You can if you're sort of prototyping things and you try something, if you're interactively at your console or terminal, you're interactively creating some of these classes, and you say, okay, I want to get rid of this one. You can use remove, but generally speaking, remove is not something you typically want to do in your code. So let's take a look at introspection. We need a way to sort of know what's in our slots and what slots we have, for example. So you have two functions. One is called get slots, and the other one is slot names. Now get slots gives you a little bit more information. So if I have A and if I say get slots of A, then it tells you that there's a slot S1 in A and that its type is numeric. But if I say name slots, it just says, okay, you have a slot, A has a slot called S1. Now it will list all, in this case it's only one slot, but in general it will tell you all the slots. Now remember, these slots are like data structures. This is where the data is in these slots. You're going to have methods that you're going to be defining which act upon these instances of these classes. And where do these methods get their data? Well, they get their data from these slots. So we have methods acting on instances that get the data from the slots. Now, there's a function called extends, and extends can have one argument and two. If there's one argument, it returns all the subclasses, including itself. And on the other hand, if it's true, it just returns the subclass of the second argument. So just to show you, if I say extends B, now remember B inherits from A. If I say that, then it says, okay, here's B, and it's the inheritance path that inherits from A. So sometimes you need to check on this. If you say extends BA, that's true because B inherits from A. But if I say extends AB, that's not true because A does not inherit from B. It's not symmetric. It's directional. So B inherits from A, but A does not inherit from B. So you can use the extend functions to try to get this. Now, there's a library function for the bioconductor called RBioInf, and this has some utility type things. And so, for example, suppose you want to know what the superclass of B is. The superclass of B is A. That is to say, B inherits from A. And if I ask what is the subclass name of A, it's B. So sometimes you need to know the subclasses of a class as well as the superclasses. These are not in general defined in R. These are only if I load the package RBioInf. So they're in this package, which is part of this collection of packages in Bioconductor, which is the group of packages that does bioinformatics. Now that's not to say there aren't packages there are packages not in Bioconductor that do bioinformatics too, but this is a huge collection of packages that does bioinformatics and Bioconductor. By the guy who wrote this book, gentleman, was one of the main authors of the Bioconductor suite of packages to do bioinformatics. And currently, I think he's chief scientist at Genentech or something like that. Now you can use getClass and extends on these built-in functions, and you might be surprised what you get. So what's a built-in? What is a built-in class? Well, matrix. Matrix is something that you don't write. In other words, it's baked into R, but we can still learn about it. So getClass and extends can be used in this case. Now, typically what happened is the R object matrix was actually around well before there were any S3 or S4 classes. In other words, it occurred before any class structure was written in R. Now, R has always been sort of a functional programming language. That's always been true since the beginning. But in terms of object-oriented, that's been around for a while. Around 1990, I think S3 classes started coming in the original S language, and because R actually, as we now know it, didn't occur until later in the 90s. But if you had these structures which were previously defined, then what happened as R developed into a class system is all of these data structures like matrix became objects in a sense of with a class. And this was done by a method called set old class. And set old class is different from set class. Set class is what we created. We created a new class. But if you had an existing object, you can use set old class to take an old object that was not a class and put it into a class system. And that was true of matrix, for example. So if I'm looking at get matrix, you might get the class of matrix. Then this tells you that this matrix is in the package methods, and there are no slots. In other words, this class wasn't defined with slots, but it actually does extend several other types of structures. It extends an array, a structure, and a vector. You can think of it as, in terms of extending an array is like a multidimensional matrix. So you could talk about a three-dimensional array. Well, a matrix is a two-dimensional array, right? So I can think of a matrix as having rows and columns. It's two-dimensional. But suppose I had rows, columns, and depth. So if I pick any particular, I have a third dimension, I could slice through it. That would be, any slice through would be a matrix. So I have an array, and more generally, you can have a more general data structure. There's a more general data type structure. There's a structure type object, which is more general than the array and matrices. So again, within the class hierarchy, you're getting further extension. That's why it says distance equals 2 and distance equals 3. Distance equals 1 is actually array. And then the final one is a vector. And in a sense, a vector is the most general thing because you can shape it into a matrix, you can shape it into an array. And in that sense, it's very general. So you may be surprised that a vector is in that class hierarchy, but it is. So if I say extends with a single argument matrix, then this is giving the this is given that the matrix inherits from array, inherits from structure, inherits from vector. If you take a vector and put a dimension attribute on it, you can create a matrix out of a vector with a dimension attribute. Are there any questions? Okay. Okay. There are also we've talked about this a little bit before, and I don't think I actually have examples here. Suppose you want to know whether something is a class. You can use isClass to determine, logically whether or not an object has been defined as a class or not. There's also isS4, and that tests whether or not the object is a S4 type class. So that's a more specific test. So if you had a class, isClass is more general, and is.object is even more general. That almost always works, and so that's not necessarily a good differentiator in terms of if you need to know specifically, well, is this an S4 class? Because if it's an S4 class, you may take certain actions, which would be different than if it's, say, an S3 class. You can also do coercion from one class to another. So, for example, if I say I want a new instance of class B, I can do that. And then if I use the as function, we can use as to coerce. And I can say as, I want to take my B and coerce it to A. And so if I coerce it, I actually find out that now it's an object of class B and has a slot S1 of 0. So there are reasons why you want to coerce an object from one class to another, and in R you can do it. But you can also coerce part of a class. That is, if I use, if I create a new class A, which has a slot value of 20, and then I say as I want to coerce it to A, but I want to change the slot value because by default it'll be 0. And if I do that, notice that the slot's 20. So you can actually coerce part of the class. Now I don't know how important that is, but again, there are occasions where you want to do this. Okay. Now I was going to skip this. I just want to mention that sometimes you have a matrix. There's a class called graph AM, and the AM stands for adjacency matrix, and that's a type of matrix dealing with graphs. And you may want to just convert that to a regular matrix. So you want to take the specialized matrix and force it into a regular matrix. And that function, you would have to, I'm not going to do that, you would have to know sort of what the edge data defaults are and so forth, and this is dealing with a graph. Now by a graph here, I mean, I'm not thinking of histograms. I'm thinking of objects and the relationships between objects. So I'm thinking of this in a more mathematical sense, that Facebook is a graph in the sense I'm talking about. You have nodes, which are people, and you have relationships between people, which are edges. And so if you want to look at these types of relationships, I don't know if this is going to work or not, but this is something we're writing, but it may not work. Yeah. So this is sort of a system we're developing. So in our case, these are the slots, these are the files, these are the collaborative people working with us. So if you take this code, this is traffic data, and suppose I execute this code, then this is what I'm talking about. What this is this is a graph showing a node, and the thickness of these lines is showing the strength of the relationship. And there are actually 4 of these, and these are actually over time. This is, if you think about how does if you have, in this case, you have traffic monitors, and it's looking at the relationships over time of traffic patterns. And so these 4 graphs are at 4 points. You're slicing it at 4. It's like streaming data, and you're slicing it at 4 points in time. But you could think of Facebook, and you could think about if you take a snapshot, you have this incredibly complex graph, and it's dynamic. It changes over time. Now, the difference is that the algorithm I used here was actually what's called a Markov model, and we have a course, Stat 763, on stochastic processes, and we also have a course on bioinformatics, and some very important Markov models underlying a lot of the theory behind, for example, gene interaction networks. And so this is EMM means extensible Markov model. A Markov model typically has a fixed number of states. And then you're looking at, if you go from one state to another, you're looking at what are called transition probabilities. You have a state, and how do you go from this state to another state? But these models are different in that the number of states is not fixed. In other words, if you think of Facebook, the number of nodes change. You have people joining Facebook, you have people dropping out. So the number of nodes is constantly changing over time, as are the relationships. And so you can't have a fixed, a model that assumes a fixed number of nodes just isn't right. And so you need a more dynamic type model. And so this particular case, this R package, actually. It's called aura-EMM. Does not assume a fixed number of nodes. And so it extends the basic Markov model in that sense. So if you take stat 761, you're going to get a vision that's different because you're going to assume there are a fixed number of states and you have transition probabilities between states. But in a lot of cases, we need to extend those Markov models into something like this. So it's kind of an interesting thing. And at any rate, by the way, yeah, this is the way our interface works. And you can sort of pop in and out. Our interface also works on an iPad. And you need something like this. If you try to actually do RStudio on a tablet, it doesn't work very well because you've got 4 windows on a small tablet, and it just doesn't work. That's actually why we have things sort of popping up and disappearing. So if you want to see, this is the actual R workspace, and these are actually the files. So I don't know if this runs. This is, let's see if this, yeah. So this is actually a SAS program, and this is the SAS output, which is actually easier than using X11 if you actually have had 521. So, and again, if you have an error, then this is the log file. Oops, let me go. Yeah, that's the log file. So, at any rate, going back. So I'd like to talk about creation of new instances. You know, how do we do that? Well, we already know how we do it, sort of, right? We use the new function. You have a class, and I want a new instance of class. I use new, and I could just say I want a new instance of A, and that could be it. And it takes default prototype values, or I could override the prototype values. So here's an example. Here's an example. You know, I could create a class called ex1. Oh, and let me back up a minute. Let me back up a minute and talk just a little bit. Ordinarily, when you do this, we've taken several examples, and we can just sort of create these prototype instances with the new function. But a lot of times, for more complex cases, you want to have your own initial, what's called an initialize function, which initializes, and that may be fairly complicated. So for example, on your one-way example, you would probably write an initialize function which would do some of the initial work in terms of, well, what slots do you need? Well, you need slots for your data, which might be a list that would have the different samples as each component. You might want to generate slot values for the degrees of freedom. You know, you could compute that by knowing the length of each of those lists. So that initialize function may actually compute the values of some of the slots. In other words, you may give it some basic data, and your basic data may be, in your one-way case, it may be, okay, I'm giving you a list, and that list has components. Each component is a sample. You know, the first one has 10 observations, the next one has 12, the next one has 9, and so forth, all measured on the same variable. And so then you want to compute other things like the sum of squares, among and within. So if those are slots, then you don't pass the instance the values of those slots. You compute them. So if you're writing an S4 class, that you would almost certainly, if it has any complexity at all, you'd want this initialize function. So typically we would use an initialize function to do this, or initialize method. But you can also, of course, as we know, you can supply values to the new function. Now, I've already told you that prototypes can be set up by the call to the function prototype, but I also mentioned that you could also use a list as opposed to a prototype. So for example, I did that. So I want to create a new example. And then if I get the class, well, if here I'm going to assign get class, I'm going to assign that to B class, and then I can extract the prototype from it. And the prototype, if I assign that at, gives me direct access to a slot. So notice that I have, if I have the class of EX1, I can then get the prototype using that at symbol, and that gives me the prototype. And in general, I can access slots directly using the at symbol. So you're going to see these at signs various places in the text. And so that says it's a type 4 object, and there's an attribute S1, which is this. Now actually, this is a little bit of a problem, because how did we compute S1? Well, we computed S1 as a random normal sample of 10. So I have R norm of 10. Now what does that do? That creates a sample of 10 from a normal distribution of mean of 0 and a variance of 1, right? That's the default. R norm, if I don't give it any other values, it will take a standard normal distribution, a mean of 0 and a variance of 1. It will get a random sample of whatever you specify, in this case 10. But the problem is it's now defined as an attribute. So if I say B, you know, that's the value of B. And let's do another one. Here's B2, and let's look at B2. Now what do you notice about B1 and B2? Well, B and B2. What do you notice about them? Is that what you really intended? Do you think? If I created another instance, don't you think that I really wanted to have another random sample of that? Why would I want to create another instance that has exactly the same? I mean, those two samples are identical, right? That's because it's defined as an attribute. So that wasn't probably what you were expecting. That B and B2 have the same exact. I randomly sampled. I would have hoped that B2 had a different random sample, but it didn't. That is because we use the prototype function here. If I would have had that as a list, that would not have happened. So there's a way around it, but I'm just pointing out that instead of having prototype there, if I would have put list there, so I can have one component that's an element of a list, then this would not have happened. Actually, I don't think it happens. I haven't actually tested it out. I'm pretty sure it doesn't. Okay. So a prototype can be defined by the prototype function, but it also can be defined by the list function. In both cases, you have named components. So if the prototype function, I have S1 as a named component, and if list, I would have S1 as a named component. Now, a lot of times we'll have a constructor function, like make example. And so a lot of times we don't just use new. We actually have some constructor function, and then so let's take this function. Let's take a look at that function. It says, okay, we have a function which has no arguments. We're going to create a new instance of EX1. EX1 is the class. And I'm going to call that OBJ, object. And then object at S1, that at says I want the slot S1 from the instance OBJ. And I'm going to define it to be R norm with 10, just like before. Except it isn't just like before, but so I define that function, and then I define B2. And then B2 should be an instance of that, which I didn't mean to type there. I meant to type over here. Okay. And you notice that B2 is different. By doing it as a constructing function, that's another way I can get around the problem of I really want different random sample for my different instances. So constructive functions is usually the way that you would think that instead of just using new, that we actually create instances. New is an easy way if you're just sort of playing around at the terminal, but if you're writing code, you probably want a constructive function where you define slots that way, instead of just defining as either the prototype or in the new. There are two ways we've talked about. You can define these slot values as part of the prototype, or you could define, and that's fine, those would be the defaults, and we can override them by defining them with the new with arguments for those slots. But the other way is to have a constructive function where we override the slot values. And they really do override the slot values. Okay? So if BB is of class B, we get the class of B, and then we actually look, again, I'm just showing you this at function. A prototype shows you the values that you need. What those are the prototype values. Okay? But perhaps the better way, as I mentioned, of doing this is with some sort of initialize method. And so in this case, we already have a class we've defined for A, right? Suppose we define another class called W, which has a slot C1, which is character. So let's define the class W. And now I'm going to define, and this may be the first time we've done this, I'm going to define a class WA, which inherits from A and W. I don't think we've done that before. So we do that. Okay? So you can see that WA extends both A and W. Now suppose I create an instance of A with S1 equals 20, and I define an instance of W with C1 equals high, and then I say new. Now this is one way we can do it. Since we've defined these two instances, I can now say I want a new WA object of class WA, which gets its information from A1 and W1, which are instances of A and W respectively. That's one way we can do it. But again, this is kind of restrictive, but we'll go ahead and do it. So that defines a new object with those slot values. So we can actually put those arguments, which are the instances of the class, and those are unnamed arguments. They're simply the instances of the class that our new object is going to inherit from. But that's still not an initializer function, so this is what is the more important way to do it. Let's set a class XX, which this class XA has a slot A1, which is numeric, a slot B1, which is character, and then I have a prototype, which gives the value for A1 of A and B1 as high there. So let's define that class, and those are the default values for the slots. So we'll define that class, and then if I create a new instance, what is that going on? B1 is missing. both defined. I'll have to look at that more. At any rate, here's the key thing. I'll have to take a look at that. I'm not sure why that's happening. Does anyone see why it's happening? I'm talking about why that's not working. I mean, I could say B1 equals something, but I have some sort of syntax error I'm not seeing. But it didn't give me a syntax error up here, so I'm not sure why that's not working. Because B1, both A1 and B1 are defined as a default value. They're defined correctly. A1 is numeric, B1 is correct. So I'm not sure why that's not. Now, what I'm going to do is now have an initiator method. And this is probably the most common way of doing it. So we're going to have an initialized function. We're going to have an initialized method or function for XX. And it's going to take the object. In this case, what it's going to do is have a function that you can pass it objects like B1, and then you can compute other slots within the initialized method. So to go back at our one-way analysis variance sample, you may have an initialized method that actually you pass it a character, a list of named objects, one object for each sample. So if you have 3 groups, you would have 3 vectors representing those 3 groups. So you'd have like A equals some C, some vector of values for the first sample, B equals some vector of the second values, C equals some vector of third values. Okay, and that's maybe all you pass it. But then you can, if you have other slots defined for the methods, you can actually compute them from the data. So in this case, we're going to pass it B1, and then we're going to compute A1. So what happens is that if we now execute this method, then we're defining an initialized method for XX, and the dot object is the object you pass it. And then in this case, the dot means that if you extend this method and you want to define other arguments, you're free to do that, and it just passes it through to those others. We had the dot before. It's one of the more confusing things in R, and it can cause huge debugging problems unless you're really good at R. So, you know, you'll see in some of the more complex examples of R, the dot is used, but it's just simply a way to extend a class, let's say, and then pass. You know, these are not defined for the classes that you've already defined, but arguments can get passed through to this new class. So in this case, the call next method, what the call next method will do is it will call back to the default where it takes the object, it sets B1 to B1, but A1 gets computed at in-char compute actually calculates the number of characters in B1. So if, for example, I run this piece of code, then I'm saying new XX, and B1 is Yasser. So when I create it, then A1 gets defined as 6 because this is what gets passed, but it's simply counting that there are 6 characters in that. So this initialize function is counting the number of characters in B1 which got passed to it. So here we have an example of an initialized function. This is a rather trivial example. And if I had you write an S4 class for your one way, it would not nearly be this trivial. Okay. How are we doing time-wise? Okay. I want to do one more example. And yeah, okay. I'm going to do an example where I have a class that I'm going to define called capital, and the representation is simply going to be a string that's character. So I'll run this class. And then I'm going to create something called a counted capital, which is going to have a representation of length, which is numeric. So in other words, counted capital is going to extend or inherit from capital. So this particular class inherits from the first one above it. In other words, it says contains capital. Think of it as inherits from capital. And so, and then now it's going to have an additional slot called length. And so I'll go ahead and specify that. Now I'm going to have an initialize method for each of these. Okay. Now, what is my initialize method for capital? Well, capital only has that one string, which is character. And the only thing that's going to happen, you know that there's a function there. Do you see this function right here? What do you think that function does? Think of it as TO upper. To upper. It takes a character string and it makes it uppercase. So everything that's not capped, it caps. So if you send it lowercase stuff, it capitalizes. So that's what my initialization is going to do is it's going to convert everything to capitals. And then it calls that next method, which is going to ultimately create the object. So we can set this method and execute it. And now what is the what do I have as my initialized method for counted class? Well, I'm going to call next method, but then it's going to actually count the number of characters of that object string that I created in capital. And when I say call next method, it actually goes up to the, in other words, the next method is now in capital, not counted capital, because counted capital inherits from capital. So I now can execute this, and then I can create a new string. And so notice what I created a new instance of capital, and I sent it an argument string equals mixed with upper and lower cases, but the actual end result is all uppercase. Notice here, not uppercase, but the end result, when I created the instance, it converted it to uppercase. If I send that, if I create a new instance of counted capital for that string, let's see what happens. So if I do that, now I have a second slot, which actually counts the length of it. It took it to uppercase because I called next method, but it also computed, it computed the length. Okay. And then finally, if I have a string with 2 in it, notice that I have mixed and the second argument here, then it actually is vectorized in the sense that it tells me the first one is length 5, the second one is length 7, and these are the slot string. So when I compute the lengths, where is it? In carry, if it's actually a string that has the string has elements, so it's a vector of characters, then it actually operates on that vector, and it counts how many each have. Okay, so that's pretty cool. So I'm going to do one more. I just want to talk briefly about validity. I did not put any. Maybe I should, but one of the things you can do, if you look early on, I think at the very, see, I'm at line 211. If you look very early on, notice I talk about validity. Validity is a function that checks the validity of the class entrance. In other words, if you typically you should write a validity function which checks. If you create an instance, you want to make sure that it's correct. So you want a validity check to make sure it's correct, and that's what this function does. I didn't give an example of that, but for good programming practice, I would recommend you do that. So at any rate, I think there's too much to finish this. I think I'll stop at this point and just sort of ask once again. I wanted to mention one other thing about the exam, so let me just stop here and take a minute. In terms of the exam, well, let's see. Yeah. I want you to look here. There's one other thing I wanted to mention about the exam, and that is you also should study this, at least the parts we talked about. We did not, in other words, this is what your homework is, but I also want you to study this. Now, part of this deals with creating a package. I'm not covering the part that's talking about how do you create a package. But the examples about how we do all this, again, that's behind the homework, but I also expect you to know it. So I do want you to study this particular document as part of the exam, too. I just wanted to put that in here before we leave today, because I could ask questions from this also. And they also give some, besides examples on how do you do the linear modeling, they also talk a little bit about object-oriented programming. It really only talks about S3 classes. It mentions a little bit about S4, but it doesn't really do anything. But there are some examples of the S3 system, and you might want to look at these examples. They're similar to some of the things we've done. So you might want to take a look at this section. We focused on the basic workhorse of how you compute linear models, plus this section in here that talks about it in formulas and so forth. But again, this is going to be covered on the exam, and I just wanted to mention this before I leave today, or you leave. Okay, is that clear? So in addition to the chapters in the book, this document is covered, but not the stuff that deals with how do you create a package, but how you create the classes, the S3 classes, that you should know. Part of it's in the book, but this gets more concrete in how you really do it. So any final questions on the exam? Yeah.
So the exam's until like what we learned on Monday? Or is it?
What now?
Is the exam like
through Monday, but not today. Anything I've talked about, other than that little introduction on S3, S4 classes at the very beginning of Chapter 3, I think Section 2 maybe, that's fair game and sort of some general ideas about S4, but the more specific nuts and bolts we talked about today, no, it's not on it. So Section S, the fourth section is not on it. Okay. Up through the third section is on it. So Chapter 1, not much there. Chapter 2, except for those two sections I mentioned on the exceptions and graphics. Chapter 3, up through Section 3. And this Frederick Leach paper. Okay, is everyone clear on that? Okay. Well, have a nice long weekend. I'm sorry I kind of ruined it for you, partly at least. On the other hand, got more time to study. Unless you're taking off for Florida or something. Graduate students don't do that as much. That's an undergraduate thing.